students. In this session, let us have a discussion on vibration transmissibility. So consider a system of a machine which is supported by the springs and the damper. First, initially, without the spring and damper, the machine is creating or generating some vibratory forces, and it is transmitted to the foundation. So, in order to isolate the force generated from the machine to the foundation, the machine is kept along with some damping proof such as spring and damper. So the system look like this. So the figure is meant for the vibration isolation because the generated force. So let us assume the machine generates the force of harmonic nature. So the disturbing force may be considered as F cos omega t. And let's have another assumption that the vibratory motion is of single degree of freedom. That is, the movement only is in the vertical direction, up or down. So, in order to prevent the effect of the transmitter to the foundation, the machines are normally, as we know, mounted on the dampers and springs. So, the damping arrangement is done by the set of springs and the damper, so as to the transmitted force cannot be passed to the foundation. Now, the one more term you have to know in this regard, the transmissibility ratio or isolation factor. So, as we know, the machine generates the disturbing force of harmonic nature F cos omega t, and the force is transmitted to the foundation through the dampers and the springs. It is the here the transmissibility ratio is the ratio of force transmitted to the force applied. So here force applied is the simple harmonic force generated by the machine. So here the transmissibility ratio is the ratio of force transmitted to the force applied or generated. Here force generated may be indicated as Ft, and the force generated is F. So it is a ratio. Here in the equations that are derived, there are two types of forces are generated. One is by the springs, that is spring force, which is equal to S into X max. So here S indicates the stiffness of the spring, and X max is the maximum displacement by the application of the force. And second force is by the dampers, that is the damping force. So which can be equal to C into omega into X max. So here C is the damping coefficient. Now the two forces, that is spring force and the damping force, are perpendicular to each other. Then we can resolve for the transmitted force Ft. So it can be considered in the two sides of the triangle. So the hypotenuse is considered as a resultant force, that is the transmitter force. So the Ft is squaring the both component of the forces and adding and having the square root. Here we have X max into square root of S squared plus C squared into omega squared. Then we know the transmissibility ratio is indicated with the symbol epsilon Ft by F. Here Ft, that is the X max square root of S squared plus C squared omega squared divided by F. Now, first we simplify the equation. So X max maximum the displacement equal to XO into D. It is a magnification factor. Here XO equal to F by S. So substituting F by S into D. Here again the transmissibility ratio formula, substitute the X max equation. So the equation becomes like this. Then the D can be taken outside. Sorry, it's on simplifying, dividing the terms by S squared. So the equation becomes like this. Here again, it can be simplified. Here, the C omega by S can be replaced by 2C omega divided by CC and omega n. Here, the C by CC is called damping factor, damping ratio. Here is substituting the C omega by S equal to these terms. So the equation becomes like this. Again, you put in the equation. So the equation like this. Then the substitute the value of D in the epsilon value. Here the equation becomes like this. So this is the formula for the vibration transmissibility. Here, if a system does not have any damping, so the damping coefficient, the C can be equated to 0. So again the transmissibility becomes like this. Here we can have a notification when the omega by omega n is greater than 1, the epsilon value will be negative. So the negative transmitter ratio indicates that there is a phase difference of 180 degree between the transmitted force and the force generated, that is a disturbing force. Again, when the omega by omega n greater than square root of 2, and the epsilon is to be less than 1. Here it is independent of the phase difference. So practically for our convenience, the transmitter ratio formula can be rewritten here 1 by omega n whole squared minus 1. Here next this the formula for the transmitter ratio when damping is 0. Next we look into the graph. So this graph is plotted between the transmissibility on the y-axis and the ratio omega by omega n on the x-axis by different values of damping coefficient C by Cc. So we have these curves. So what the inference we have had from the graph is, first point, when the omega by omega n is greater than is equal to square root, so all the curves passes through the point where the epsilon is 1. Here as indicated. So when omega by omega n equal to square root of 2, that is this point, all the curves for all the values of the C by Cc ratio, the epsilon is 1. Epsilon is 1. Second, for epsilon value, omega by omega n is less than square root of 2. Yes, here consider that here less than 1 by 2. Here the C by C transmissibility is always greater than 1. So always epsilon greater than 1, what transmissibility is greater than 1. So what here indicates it, the transmitted force is greater than the applied force. That is the idea. Then third case, omega by omega n is greater than square root of 2. Square root of 2. So here, notice this point, greater than square root of 2. Here, the transmitter ratio value is greater than 1. So less than 1. Less than 1. Here, what it indicates, the applied force is greater than the transmitted force. So here the vibration isolation is possible only the omega by omega n greater than square root of 2. This is the case where we need the isolation. So whenever the omega by omega n greater than square root of 2, so the damping is very dangerous and detrimental because beyond the value the square root of 2. So only when the omega by omega n less than square root of 2, the isolation dampers need not be provided, but sometimes, many times, it's provided to limit the resonance conditions. So the resonance is the force, the frequency of force equals the natural frequency of that component. So to avoid the resonance occasions, the dampers are provided. So this is the information that we are obtained from the graph. So let us have here a small example, a problem by which we can know the transmitter ratio. So the mass of an electric motor 125 kg and it runs at 1500. The armature mass is 35 kg and its center of gravity lies 0.5 mm from the axis of rotation. The motor is mounted on 5 springs of negligible damping so that the force transmitted is 1/11 of the impressed force. Assume that the mass of the motor is equally distributed among the 5 springs. Here the motor is kept on the 5 springs and the damping is negligible. So C equal to 0 and the armature is offset by 0.5 mm. Okay. First, let us have the given data. Mass of the motor M1 and mass of the armature and the radius, that is 0.5 mm, that is offset, and epsilon. Here the force transmitter is 1/11 of the applied force, that is Ft equal to 1/11 of F. So epsilon equal to 1/11 and the motor speed 1500 and the angular speed is 157.1. So let us have the first question, stiffness of each spring. So we know the transmission ratio formula, then we have the C equal to 0. So simply substituting this omega by omega n whole square minus 1. So on simplifying, and we can have the value of the omega n, that is natural circular frequency 45.35 radian per second. Again, we have the omega n equal to square root of S by M. Here we consider the motor as a whole system. So M1 motor, mass of the motor, from which we can have the value of S, that is 246,840 Newton per meter. So it is amounted to it's contributed by the 5 springs. For each spring, we have to divide the value by 5. So stiffness of each spring, 49,360 Newton per meter. The second question, dynamic force transmitter. Here, as we know from the formula, the armature is offset by 0.5 mm and during the rotation, it creates a centrifugal force. So the centrifugal force F equal to m omega squared, or we have the general formula. Here the mass is denoting the mass of the armature. So F m2 omega squared r. So we have the centrifugal force value. Then Ft equal to epsilon into F. So 1/11 into 432, 39.27 meter. Then the natural frequency of the system, omega n. Already we have found the natural frequency, so 45.35. So I hope all of you understand the vibration transmissibility. Thank you.